Which brings us to question 8. Okay, so you had this oxygen coming out. What happened as the oxygen filled the air? So the Earth oxidized. Well, that's the simple answer, but what does that mean? You know, it means it changed in a predictable order. And we can see how oxygen and light change things by doing experiments. And different forms of oxygen have different effects on different colors. Some colors appear, some colors disappear. So I'm going to show you an example of each. Now, as Earth went over time, and the main thing I want to show you, this is billions of years ago on the x-axis. Okay, so as we look back in time, what do we see for the oxygen? Well, we see there were basically 3 eras. There was a time when there was no oxygen. You see there's no line here. Then photosynthesis happened. Oxygen went up. Simplification, but it works. And it went up to about 1% of today's levels. So medium oxygen time. And then we hit right here. It's at the very right end of the graph. Oxygen goes up again to close to today's levels. And right after that, we see the first fossils. This looks very suspicious. You know, so it looks like oxygen is doing a lot of things here. So what is oxygen doing, especially right here, when oxygen is doing all these things? For one thing, if we look around and when we see these big oxygen jumps, you see these orange BIFs. BIFs are banded iron formations. What it is it's a bunch of iron and oxygen that stuck together and sank to the bottom of the ocean. So it looks like those two things might be connected. So you can see how oxygen changes things by seeing how it changes colors. So oxygen makes some colors appear. If you're making indigo dye, what you do is you mash indigo plants up, you heat them, and you wait. And this results in the nice blue dye in your pot. Oxygen is what is actually producing the blue when you look at it. So oxygen is changing the molecule. Here's the indigo plant, and that's a nice color, but it's not exactly indigo, is it? The indigo plant contains the molecule that turns indigo, but it's not yet indigo, you know. This is the form that it is in the plant. And what happens when you heat it up, the water chops that hexagon off. It's actually a sugar. And it cuts that sugar off, and it makes Doxil, which is this thing right here. You see how that looks like that. And then oxygen results in 2 Doxils forming a bond. This makes the color indigo. Okay? So, you need a special plant, and you need oxygen. Oxygen is making that color appear. If you've ever used bleach to remove a stain, then you've used oxygen to make a color disappear in a slightly different way. This especially works for wine, coffee, and tea stains. Interestingly enough, stains made by colors from life. Okay? Life color stains. They're readily removed by bleach. It's because of this chemistry, because bleach is an oxidizer. It's more powerful than O2 as an oxidizer, but they're doing basically the same thing. They are destroying the colors, and it turns out that these colored pigments are destroyed by that high oxidizing power. So basically on the ancient Earth, when oxygen came in, you had a bunch of stuff happening. You had a bunch of things changing. Some molecules were destroyed, some molecules were produced. And in particular, the sulfur and hydrogen-rich foods that the bottom layers of the Winogradsky column ate, those were destroyed. And so they lost their ability to live in that way unless they avoided oxygen. So you can see how light and oxygen cause colors to change if you look at different colors. Now, here we have the Immaculate Conception, Velázquez, and you have a red lake carmine robe in the middle there. That red lake has definitely faded over time. This isn't the right color on the projection, but even this you can probably see is faded. This is a red lake that is like carmine that we showed, and over time it has faded to become less red. Indigo also has a problem. It's not a very good dye for long-term storage because it will fade under duress. And as you know, if any of you are wearing faded blue jeans right now, that's indigo that has faded for one reason or the other. If you look at Titian's Bacchus and Ariadne, you can see a lot of the different colors. Here's the white lead that we were talking about before, the lead carbonate. This is vermilion, which is a mercury mineral, and realgar, which is an arsenic mineral. These colors are very bright and they stand out even here. And also, by the way, that's ultramarine. Apparently, the patron had a lot of money because the whole sky was blue from the ultramarine crushed gemstones. But if you look over here at this sash, that's a red lake pigment. And notice how much more translucent it is. So if you want a translucent color, you want to go for a carbon-oxygen structure made by life. If you want a really bright red, you want to go for the sticky metal, the one that will probably poison you if you use too much of it. And this is a general rule that you can probably use when you're looking at most things in art. So some things are stable, some things are not in different conditions. And so if we look at all the chemicals in the earth and we map out how reactive they are to oxygen, we can see how the Earth's chemistry changed. These are mapped out by what's called redox potential. And for our purposes, it's how reactive is it? How reactive is it to oxygen? And when a certain chemical reacts, it moves from being the non-oxygen form, like CH4, to the CO2, which is the oxygen form. So I actually have it circled right here. Sulfur moves from being SH2 to SO4 when you reach this redox potential. And the important thing is, as the Earth filled with oxygen, its redox potential went up. That means that you can look at this and you can say, oh, early on, the SH2 changed to SO4, and all those poor little microbes lost their SH2 lunch. The next important thing that you can see, iron changes from iron plus 2 to iron plus 3. Iron plus 3 is insoluble in water. Remember what happened at the bottom of the graph when we saw oxygen go up? We saw a bunch of iron oxide type minerals at the bottom of the ocean. We saw the banded iron formations. That's evidence that this happened. So this is great. This fits with our theory. It's bad for life because life uses a lot of iron. It's a very useful metal. In fact, we still use it, but we have to scrape for it now. Before it was much more abundant. So the iron went away, but the good news is, after the redox potential raised a little more, we hit that line. And at that line, copper changed from copper 1 to copper 2, which means it became more soluble. So the periodic table giveth, the periodic table taketh away, and what we have is we have iron going away and copper coming in. And you can represent this on the periodic table. You can draw on yours if you want. If you can draw this arrow. If you just draw an arrow from iron to copper, this is what happened over time. Iron, cobalt, and nickel especially disappeared. Copper and zinc appeared. And this has to do with their reactivities with oxygen, which have to do with their exact place on the periodic table. So it all comes back to that. This is predictable from their redox potentials. So as the Earth oxidized over time, it changed in a predictable order. The weird old foods were oxidized away. Iron rusted out of the oceans and became banded iron formations locked away. Copper appeared for life to use in that order, in a predictable order.